Show that 5 is a 0 of p of x equals x cubed minus 19x minus 30. Find the other zeros of p, and then sketch its graph. To show that 5 is a 0 of this polynomial, we can use synthetic division. The coefficients of the polynomial are 1, 0, because there's no x squared term, negative 19, and negative 30. We put 5, our potential 0, on the outside, and we go through synthetic division, hoping to get a remainder of 0. So we bring down the 1, we multiply and add, we multiply and add, we multiply and add, and sure enough we get a remainder of 0. This tells us that 5 is a 0. It tells us that x minus 5 is a factor, and then it tells us that the leftovers, when we factor out x minus 5, are going to be x squared plus 5x plus 6. Now we can use the unfoiling method to factor the leftovers. So we still have the x minus 5. Now we're looking for two numbers that have a product of 6 and a sum of 5. Those numbers are 2 and 3. So now that we have the factors of our polynomial, we can write out the zeros, which will be 5, negative 2, and negative 3. Now, in this case, I'm actually going to make my own x and y axes. And the reason I'm doing this is because we have a y-intercept of negative 30, and that is outside the bounds of the template I have for an xy plane. So I am going to draw my own one now. And we know that we need x values that go all the way up to 5 at least. So let's do 2, 4, 6, and 8. And then on the negative side of things, we need to go at least all the way to negative 3. So negative 2, negative 4, negative 6. I could go further if I want, but I don't think we need to. So I'm actually not going to label my y-axis yet. I'm going to do that in just a minute. First, I'm going to plot the zeros. So we've got 5, negative 2, and negative 3. We know that we're going to have a y-intercept that's as low as negative 30. And that's going to tell us that in this interval right here, the graph is going to be below the x-axis. But we don't know what's going on here. We don't know if it'll be above or below, and we don't know how high it'll be. It could be that we get something that's much bigger than 30. It could be 60. So before I go and label the y-axis to include 30, I want to get a point in between these two numbers so that I can figure out what my scaling needs to be. So we need a point that has an x value between negative 2 and negative 3. We're going to do negative 2.5, which is going to be slightly annoying to evaluate the function at, but we can do it. We'll want to use a calculator, but this is fine. So we bring down the 1. 1 times negative 2.5 is negative 2.5. Adding gives us negative 2.5. When we multiply, a negative times a negative is a positive, and 2.5 times 2.5 is 6.25. When we take 6.25 and we subtract 19, that gives us negative 12.75. We can multiply this by negative 2.5 to end up with negative 31.875. Oh, sorry, positive 31.875, my mistake. And when we add these together, we get 1.875, which is just a little bit less than 2, which is great because that's not a huge number. So because the number that we need to make sure is on our y-axis is negative 30, we can go down by 5s, so that'll be negative 10, negative 20, and negative 30, and then above 10, 20, and 30. So we know that we've got the point negative 2.5, comma, positive 1.875. So that's very small. And then we have a y-intercept of negative 30. That's going to be all the way down there. And so we can see that the graph is going to look something like this. And looking at the end behavior, it's going to be the same as the last example, going up to the right and down to the left. And so our graph is going to look something like this. This graph is accurate as far as the intercepts are concerned, and as far as the intervals where we're above and below the x-axis are concerned, as well as the end behavior. The thing that's not necessarily accurate is this local minimum down here and the local maximum up there. We would need calculus to figure those out, so you'll have to wait until at least next semester to do that.